Hey everyone, Dr. P here, and in this video we're going to take a look at the kinetic molecular theory of gases. So, the kinetic molecular theory of gases is the theory that we use to explain why gases behave the way they do. Remember, the physical laws, such as the gas laws, the ideal gas law, describe behavior but don't explain it. We need a theory for that. So that's our kinetic molecular theory. KMT. All right. So what are the features of kinetic molecular theory? Well, we have the following assumptions. First of all, the gas particles are small. Small compared with the distances between them. So we'll say volume of particles equals approximately 0. Now, of course, if we took all of our gas molecules and put them in one corner of the room, we would soon see that, yes, they actually do take up volume, but our assumption is that the particles are small. Particles are in constant motion. And the collision of particles with the walls of the container is what causes the pressure of the gas. So collisions of particles with walls of the container are the cause of pressure of gas. Next, we say that the particles don't see each other. We're going to assume they exert no forces on each other. That means when they go zipping by each other, they pass by with no effect. Now, if they collide with each other, they'll bounce back in a elastic collision. But if they just pass close, there's no attractive or repulsive force. And then lastly, average kinetic energy of a gas of a collection of gas particles is directly proportional to Kelvin temperature of the gas. Okay, so our average kinetic energy, not the kinetic energy of every particle, but just on average. So some will be moving slower, some will be moving faster. And this also tells us that at a given temperature, heavier particles will not be moving as fast as lighter particles because it's average kinetic energy that we're looking at. And so kinetic energy is, what is it, 1/2 of mass times velocity squared. And anyway, but let's look at how kinetic molecular theory, accounts for the different gas laws. So we'll apply KMT to gas laws. All right, so let's go ahead and look at some different scenarios here. Okay, so first we can look at pressure and volume. This is, of course, known as Boyle's law, as we mentioned before, but P equals some constant, which is, in this case, the gas constant times the number of moles and temperature, because those are being held constant, times 1 over V. Okay, so this here is constant. This whole thing, I should say, is constant. So let's take a look. Let's take a cylinder here, a container. Let's take a container, cylindrical container, and let's go ahead and we'll have a cylinder with a piston in it. We'll have this movable piston, and it can move up and down. And we'll have some particles of gas in here. They're kind of zipping around here. Some are moving just not that fast, some are really going fast, etc. And they're bumping against the walls, exerting pressure. And they would just push this piston right out of the cylinder here, unless we put a weight on it. So we'll go ahead and we'll put our our little weight there, and that's going to keep our piston from flying out. Now, if we add weight, so we'll add weight to piston and decrease volume. So we'll have two little weights here. And we'll see that our particles right, 1, 2, 3, 4, 5 particles here. Our particles will hit the walls more often. In fact, at this lower volume, the particles will hit the walls often enough that they'll exert enough force to support that second weight. Okay, so we had to push and on our piston here in order to decrease the volume, and that additional force over area is the pressure. So we have an increase in pressure because the particles are hitting the walls more often. All right, now pressure and temperature. I believe this is Gay-Lussac's law. We have pressure equals nR over V which of course is our constant here, times T. Pressure is proportional to temperature. So we can go ahead and take our piston, got our weight, and we've got our five particles there, and we will increase the temperature. So what's going to happen? Well, our molecules are going to be moving faster. Our gas particles are going to be moving faster. Some of them won't be moving faster, but some of them will be moving faster. So this average kinetic energy, remember temperature is proportional to average kinetic energy of the molecules, so we're not increasing the mass of the molecules, particles, gas particles, but by increasing the temperature, we increase the average kinetic energy, we have to increase their speed. So the speed of the particles increase. And so the particles will hit the walls both more often and with more force. The result being that we have to increase our weight in order to increase our weight on our piston here in order to keep it from flying out of the cylinder. So that's our increase in pressure. We have gas particles colliding with the walls of the container both more often and with more force. That's because they're moving around faster because we heated things up. All right. Now we have Charles's law. Oops, I don't want to say Charles' law. I want to say Charles' law. I don't want to write Charles' law. I want to write volume and temperature. Sorry about that. So volume equals nR over P. That's our constant, times T. And so we'll go ahead and take a piston here. In our cylinder, and we'll have our gas particles, and we have some weight here keeping our piston in place. That's supported by the pressure of the gas molecules. We'll increase our temperature. And what happens? Well, the gas molecules, their kinetic energy increases. So again, the speeds of the particles increase. And so what happens is, you have these guys, it helps make sound effects, by the way. These guys are moving around much faster. That guy's moving around really fast. And so our volume will increase until we get to the point where the volume gets to a point where the collisions are less frequent and they're infrequent enough that this weight is supported by the collisions. So when we heat things up, we have increased speed of particles, so they start hitting the walls more often with more force, and that will push up our piston here until it gets to a point where our pressure is, our pressure hasn't changed. I mean, it'll happen gradually as we increase the temperature. And so again, the volume has to increase here in order to keep the pressure constant. Okay. All right, so we allow the volume to change and the pressure is going to be kept constant. We just have the one weight there. All right. Now there's one more that we haven't looked at yet, and that of course is number of moles, volume and number of moles. That was Avogadro's law. So let's go ahead and take a look at that. So V equals RT over P, that's our constant, times N. And so if we have our piston here, and we have our particles, if we increase N, we see that our volume has to increase in order to maintain pressure or keep pressure constant. So again, volume increases to keep pressure constant. So, it makes sense that with more particles you have more collisions. So pressure has to increase unless the volume increases. In fact, pumping up a bike tire or a basketball or football, whatever, inflating a car tire involves putting more moles, but we keep the volume the same, and so pressure actually increases. If you blow up a balloon, well, there the volume has to increase because the pressure is relatively constant, constrained by atmospheric pressure and a little bit by the elasticity of the balloon. But anyway. One more thing to note, and that is that for mixtures of gases, that is, when we're looking at Dalton's law of partial pressures, kinetic molecular theory assumes that gas particles are independent and have no volume. Thus, the particles of different gases look the same to the container. Okay, so KMT accounts for partial pressures. All right, again, we're assuming that the particles have no volume. Okay, so it doesn't matter what they are because they have no volume. They're little points. And then they exert no forces on each other. So again, their identity doesn't matter. So if those two things are true and it doesn't matter what the particles are, then Dalton's law of partial pressures must hold true. Now, these assumptions here are actually part of the ideal gas assumptions. So let me just make a note here. I'll do it in a different color here. So this guy here and this guy there are, so I'm going to say star equals ideal gas assumptions. And in the next lecture video, we'll take a look at cases where we don't have an ideal gas, where we have a real gas, and how we compensate for that, how we compensate for the fact that these assumptions may not be true. All right, well, that was the kinetic molecular theory of gases. And I think kinetic molecular theory is kind of cool. It can be used to describe how chemical reactions occur as well. You'll see that in Chem 1B. But for now, we'll look at it for its application with gases. So until next time, stay safe out there. Bye now.